So today we have this lecture on object detection, and I will say like this is the most interesting lecture you will see in deep learning during this course. And we have already seen like how you can do classification. That might be like maybe might have been too much challenging for you, but if you have understood that really well, then I think moving from classification to detection in itself it seems like a big deal because it's like it's not just like sample level prediction, you have to localize that prediction as well, right, where exactly that's happening in your images. So that seems like complicated, but today you will see like really it's not. It's like you can solve this task even with like a very small change to your the way you are doing classification. And we are going to cover like some advanced algorithms to do that, some of the like state of the art algorithms. And you will see that like how simple the ideas are there, how intuitive they are. And so it's encouraging because if you can understand like how object detection is done, you already know how classification is done. Then in a way, we are kind of covering like the full landscape which you need. And I think most of the problems which you will have in computer vision, you can just use these ideas, extend these ideas, and solve those problems. So you'll be, I think, will be more confident. All right. So the agenda for this lecture is we'll briefly cover the basics of object detection, what object detection is, and how it's different from image classification. And we'll start with a very simple solution. We have talked about that earlier in the course as well. So we'll look into sliding window approach. And then we will briefly cover how we evaluate any object detection algorithm. That's actually a very important topic. Followed by that, we'll have CNN-based approaches, and we will go through like a series of algorithms, and all of them are kind of related. So we'll start with like the basic CNN solution you can have, and then series of 3 algorithms which are based on this region proposal network. Okay, so let's start with the basics of object detection. So before we start, like let me give you some nice results which we can actually get today using these deep learning algorithms. So I'm showing you a video which is like completely like you can say it's a surveillance video, and it's streamlined, and this is like a state of the art algorithm. This is not like what we are going to discuss, but again one of this state of the art algorithm which can perform object detection in images. So what's being done is you take that algorithm, you have this video feed, you perform object detection on every incoming frame, and then that will give you those detections, those bounding boxes over there, right? And then we have a very simple algorithm which actually connect these bounding boxes across frames. And once you have that, you can actually track these objects. So you can say like this is, you can see like kind of near perfect, right? It's not missing any object. It's able to track them. It can differentiate between trucks and cars. Sometimes it's getting confused. Okay, but these are really impressive results. And I think the algorithm which we are going to discuss today, if you can develop those, you will be able to get these kind of results as well. So let's try to understand what object detection is. So we have seen object recognition already, right? And the idea is given an image, you have to say which class it belongs to. And we have seen these images earlier as well. So if you are doing object recognition, let's say your class is person recognition, you just need like a binary classifier saying whether a person is present or not. Okay, we have seen like a lot of variations of this problem throughout this course. Now, as we move from classification to detection, the only change you have is given an image, you will still say whether that object is present or not. And you need like one more prediction which you can use to draw this kind of bounding box on this image. Okay, so that's the localization, and that makes it like the detection problem. And for this, there are a lot of variations which you can use. One simple variation could be for this bounding box, you only need 4 different numbers. Okay, so for classification, you just need one number. It could be between 0 and 1, the probability of that object being present. For detection, you need 4 additional numbers. So those numbers could be, for example, the left top coordinate of this bounding box, and then the top right, or you can select the bottom right coordinate. So it will be like x1, y1, and this could be x2, y2. If you have those 4 numbers, you can easily draw this bounding box. Okay, so that's one variation. The other interesting variation could be you can say that, okay, you need the center of this bounding box, again, X and Y, two numbers. And then you need like, what's the width of this bounding box? What's the height of this bounding box? Again, four numbers. You can again draw the bounding box over the image. And there can be like other variations if you want to think about that. Now, again, same as object classification or image classification, you can have different variations and in this problem as well. For example, even in human detection, there might be different different variations, the problem, the way you want to formalize your problem. For example, you might have aerial images, right? Or some kind of oblique view. So in that case, even this is person detection, but the problem is quite different from when you're solving the same problem from ground view. Even for the human, you can see like the perspective is changing a lot. Okay, the objects are far away. And you can have like surveillance images or videos like this. So you can see like even the problem is same, but you might have like different kind of challenges in these two scenarios. Now, similar to object classification, where you might have multiple objects present in the image, then you need multiple heads for the prediction, right? We saw all those variations there. Similarly, you can have multiple objects for detection as well. For example, in this image, I think we have seen this image before in the class. You might have all these object categories, and then the problem will transform into like, you will say like whether bottle is present or not, whether laptop is present or not. So you will have those classification predictions. And in addition to that, for each instance of that class, for example, bottle, you need four numbers, which you can use to draw this bounding box. So you need like those bounding box predictions for all the classes or all the objects. But it's a little trickier than that because you might have multiple bottles, right? In this case, I can at least see like these three bottles here. So it's not just saying that bottle is present. You have to say that 1, 2, and 3 bottles are present. And for each bottle, you need these bounding boxes. So it's slightly complicated. Okay. And we will talk about like all those, how that can be addressed. And I mean, we have given the motivation like why we need object detection, but this is like very simple example. Let's say if you have a self-driving car, in that case, the object classification is not going to solve your problem. Okay, you need like much more stronger than that. So it could be like detection is much better than classification, because what's happening in self-driving car is when the car is driving on the road, then it doesn't matter whether algorithm can say that dog is present or not, because dog might be just like in the nearby park, right, which is visible like from the car's range. But the important is like where exactly the dog is located. If a pedestrian is crossing the road, we need to know like what's the location of that person. If the person is on the road, then the algorithm need to decide, we'll have to put on brakes, right? And in comparison to classification, if it just say, okay, person is present, that's not going to help you out because person could be anywhere. So let's try to see what can be like a very simple algorithm which can solve object detection for us. And again, we have seen this algorithm before, not from like detection point of view, but from classification point of view. But you will see like the same algorithm can solve detection for you as well. And the approach is sliding window. We have seen this like a lot. So again, sliding window I would like to emphasize, you will see it everywhere in computer vision. Because the way these algorithms work is you focus on like one point at a time, and then you have to like focus on all the other points as well, right? And a sliding window is like it's a natural algorithm which can be used. So whatever you do, you will see sliding window in a lot of places. So I can just count like where we have seen sliding window so far. We have seen like in HOG filters, right? We have seen in SIF filters. We have seen in like CNN architectures. Your convolutions, when you use sliding window there. Okay, so I will say like almost all the algorithms we have seen so far, you have required the sliding window approach. And today as well, you will see like how this is going to be useful for object detection. Okay, so a simple solution could be, if this is your input image and you want to detect like some object in this image, you can take a window, okay, a bounding box, and wherever you are placing that window, you can try to detect your object. And you know how to do that. You can just use filtering, or you can use like any other algorithm as well, but filtering is just one. And then you can just keep sliding that throughout your input image. Okay, so all the possible locations where you can place it. And then at whichever location gives you like the highest probability of detection, you can say, okay, this object is present in that particular location. So that's like a very, very simple crude algorithm, uh, which can be used. And of course, like there are a lot of interesting works out there which are actually using the sliding window approach, not just for person detection, but face detection as well, right? And HOG, as I said, like it is also using sliding window. And there are like a lot of other algorithms, just to mention these three, but it's a lot, I think used a lot in many other algorithms. Okay, so let's see how we can do object detection. And again, this we have seen, but not from detection point of view, from classification point of view. But if you think about this, this is actually solving detection for you. So this is your chair template. This is your original image. And you can just try to match this template at all the possible locations in your image. Okay, earlier we saw we can use that for classification, but now we know that this position is actually highly active. So we just put this bounding box over here and we say that, okay, chair is present at this particular location. And it doesn't matter how big your image is or how small your chair is. If you have like the perfect matching template, you will be able to localize that. Okay, so this is a like very naive algorithm which can be used. And of course, we have seen it will fail like in real world scenario because template will change. There will be a lot of variations, even in the pose of chair, or there could be like color changes, lighting changes. But the intuition will not change and the basic approach won't change. Okay, so let's try to understand how this can be done like in a more realistic setting so that the algorithm actually works, it doesn't fail. Okay, so the general approach will remain the same. You will have this input image where, let's say we are interested in person detection, and you can see like it's very crowded. So what we want to do is we want to detect all these individuals standing on the street or doing whatever they are doing. So what we do is we start with a bounding box, and we do the same thing. We scan all the possible locations. Okay. Now, while doing that, we don't use the template. Now, coming back to, we have covered like a lot of algorithms for feature extraction, right? We covered classical approaches, we covered CNN-based approaches. Now we make use of those approaches, and you will see like how features are very, very useful. So what you do from that location, you extract feature, no template matching. Okay, for example, HOG could be like one set of features. It could be SIP features. It could be CNN-based features. It's up to you. There are a lot of options out there. Then what we do is we try to classify those features. So instead of template matching, now we are doing classification, which is much more powerful than template matching. Okay, so what will happen at each location where you are placing your bounding box, you are just trying to identify using this classification algorithm whether that object is present or not. So the algorithm remains the same, the one we discussed for the naive approach. The only difference is we extract features and use those features for finding out whether object is present or not. And then some post-processing is required, which I will talk about. That's really important. Okay, so let's start. So you scan all the possible locations. Let's say this is your detection window. Let's slide and you inspect all the windows. So in this case, you can see like your window size is kind of fixed. Now the issue is the person actually, which are the persons who are closer to the camera, you can see like you need a bigger bounding box. And persons like far away from the camera, you need a very small bounding box. Okay, so now you can understand like where I'm going with this. We were talking about SIF features. So what did we do there to solve this? We try at different scales. Okay, so we created like that. That's called the pyramid, right? We do exactly the same thing. We create pyramid, and to create pyramid, what we'll do is we try to scan the images at different resolutions. Okay, so this is just showing that, okay, for the close by people, you have bigger bounding box. People which are far away, you need a smaller bounding box. And what you do is you resize your image. You resize your image, but you keep the size of the bounding box same. You don't change that. Okay, you keep reducing. And you will create like a scale space pyramid exactly the way you were doing for SIF features. So this is like a bigger resolution. and this is your detection window. Now you can see that in the highest resolution image, you're actually trying to detect the smallest scale of your object. Okay, and the idea is, if you are using this detection window, and this is, let's say, matching one particular individual, so that will be like height and width of that individual, right? But if you're using the same detection window on this scale, which is on the top, then you can see that the actual size of that person is much bigger than that. So although like this is kind of an inverted pyramid, but the scale at which you're detecting your objects, it's actually kind of reversed. Okay, so the top one will detect like bigger scale objects, and the bottom part of the pyramid will detect like smaller scale objects. All right, so one important step while we do that is Gaussian filtering, and again you have seen this, like why smoothing is really important. So what we do is we try to do some kind of pre-processing using Gaussian filter to smooth out the image, and I will tell you like the exact reason why we need to do that. So this is like your image at high resolution, and at each like step of the pyramid, you are reducing the resolution. Okay, you are going from, let's say, if it's 600, it will be 300, then 150, so on and so forth. Now, the question is, when you do that, then again, there are different ways to do it. How to go from this image to this image. One simple way could be, you can just pick like alternating pixels and you skip some of the pixels in between. Okay, so that will give you exactly like half resolution. For example, if the number of columns in this image is 600, then we don't pick all the pixels. We pick like alternating pixels, let's say odd pixels or even pixels. And then you will exactly get 300 pixels, and your image will be like just half resolution. And you can keep doing when you go down. Now, while you are doing that, what's happening, you're actually omitting those pixels. So you are actually clearly missing those out, right? If some important information is stored in those pixels, it will be gone. And that's why we need Gaussian pre-filtering. What will happen is, if you're doing Gaussian smoothing, you know that when you place a Gaussian filter at some location, you make use of values from the neighboring pixels. That's how you smoothen your image. And if you do that, then the subsampling step where you were actually skipping some pixels, even though you're skipping, but information from that pixel was actually already captured in the pre-filtering step. Okay, so now this is like something which you will get because this is high resolution, and you're reducing the resolution after smoothing. So you can see like that's the effect of smoothing, which is fine. But if you try to look at the local level feature, what you're going to get from these image pyramids. Now, if you look at this bigger image, right? So it could be like one pixel is actually maybe one stripe here, right? Or it might be reducing. And as you reduce the resolution, it could be like one pixel is just representing maybe the nose of the zebra. Okay, so that's how you're actually controlling the scale. So it's going like from 512 all the way to 8. So you have like 6-7 different scales here. Okay, so the way this pyramid construction works is so these are just showing you neighboring pixels. And even though this is like just one row, but you will have a full two-dimensional space for that. Okay, so just consider like one row of your image, which will be consecutive pixels. So, and this is just showing one dimension. So you will use your Gaussian filter, which is something like this, right? You will pay more attention to the center pixel and less attention to the nearby pixels. And then that's going to give you this pixel. So it's kind of average of all these. So this is your first like one scale of a Gaussian pyramid, and this is the next level. So in this case, you can see that whatever value you were getting for this one, you just skip that. So you are just alternating between pixel values. So you are reducing the resolution. So you perform filtering, you perform subsampling, skip those pixels, and you keep doing that. Okay. Again, if you do like Gaussian filtering of this, Again, you are considering all these pixel values to compute this one, but again, you skip in between. Okay, it's just making sure that if some pixels have important or salient features, they are not skipped over. And again, this is one dimensional. You can easily generalize to two-dimensional space as well. Now, if you think about this, the total amount of memory you require to store like this Gaussian pyramid, it's not that huge. Even though if you have like a lot of layers, let's say 3-level or 4-level pyramid, it won't be a lot, because let's say if this is saving n pixels, this is just going to be n by 2 pixels. Okay, so for a 3-level, you will see like it's just like 4 by 3 of the size of the original image. So in terms of memory consumption, it's not increasing your memory consumption by a lot. Definitely, it's never going to go to like 2x. Okay, so now the issue with like that kind of approach will be, since we are looking at this specific aspect ratio, you might have individuals in your images, something like this. Right? There will be all sort of variations out there in real world. So whatever you do, but if you have this kind of window, it doesn't matter how many scales you use, you are always going to miss these kind of detections. Okay, but again, that's just one challenge. And of course, you can try to do maybe different aspect ratios, but again, that will just increase like the computational complexity. And whatever you do with one set of aspect ratio, you will have to repeat that with a lot of other aspect ratios. And we will see later on, like in the actual CNN algorithm, how this is being addressed. Now, once that is done, you just extract features from that block, as I said earlier, and it's up to you like what kind of features you want to use. It could be classical features, it could be your deep learning features, everything is fine. Now, here's the trick here, right? So it's fine, you can extract features, but how will you classify? Right? So the way it works is, as you know that if you have to do detection, you need labels for annotations for that, right? So for training samples, you should know like what exactly that bounding box will look like. So what you do is, during training, again, you try to scan like those possible locations, and you will then have like some patches as positives and some patches as negative, because some patches will match the ground truth and some patches will not. So then what you can do is you can just collect those bounding boxes and create like a training set where you will have a positive class where person are present and negative class where person are not present. And you can just train a classifier. It could be a simple CNN classifier. It could be a SVM classifier, because in this case, you have features. And once you have that trained classifier, then you can use that trained classifier during testing time. And during testing time, again, you take the same window, keep scanning on the images, and then that classifier will tell you whether person is present at that location or not. Okay, so this is just showing some sample examples which will be used for training. So all these are like positive cases because you have individuals present, and all these are negative examples. Again, you are extracting these samples from your annotations. Okay, so then you simply train like maybe a linear classifier, something like this. It's up to you, like what kind of classifier you want to train. And we have seen like training a classifier, I think 2 different variations at least. Okay, so once that is done, we try to use that classifier to make predictions whether a person is present or not. And again, we do that at multiple scales. And of course, for preparing your training data, again, you will do that at multiple scales itself, right? So that will help. So you'll have to use some kind of threshold to say that, okay, object is present or not. Again, that's part of a classifier, you know all that. And this is, let's say, some sample result. You have this image. You again scanned all the possible locations, and then you try to classify all those possible locations. And then your algorithm might have said, okay, at this location, person is present. At this location, person is present. And that confidence level might be higher than the threshold. Okay, so remember, you need a threshold for a classifier. And if it's a binary classifier, you can say that, okay, 0.5 and above, it's a positive case. 0.5 and below, it's a negative case. So it's up to you. And again, that's like a parameter you have to decide. And let's say all these bounding boxes were detected as positive. Yeah, you can see like one issue you can clearly see, like at one location you have multiple bounding boxes, which in a way is right because all these are correct, right? you have this individual present here, but then the question is, do we really need that many bounding boxes? In this sense, the algorithm is saying, okay, 4 different individuals are present, but that's not true. We can only see one. And again, the other interesting aspect you can see, like you have some smaller bounding boxes as well, which means that you were able to take care of that scale aspect because you were trying patches at different resolutions. Okay, so that's fine. So that's like a initial step. You have these predictions, which is kind of already giving you results. But now we need to improve on this, and that's called post-processing. So we need to get rid of like these additional boxes. Okay, so let's see how we can do that. So as I said, you have multiple detections, and that's not good. So what we use non-maximum suppression, and we have seen this algorithm before. If you remember, like your edge detection algorithms, that's exactly what we were doing there. So the high-level concept of the algorithm is not going to change. Okay, it will remain the same. It's just a different kind of application. So if you remember, like from edge detection algorithms, what we were trying to do is at any given location or any pixel location, we were looking at the neighboring pixels, right, in the direction of the orientation. And if the magnitude of this edge being detected is greater than the neighbors, we say that this is an edge. But if it's not greater than these two, we say this is not an edge. So it's kind of you're suppressing if it's not like dominant in the neighborhood. Okay, so that's the name like non-maximum suppression. If it's non-maximum, we suppress it. So the idea remains the same, but what we do here is it's like slightly modified algorithm. So whatever detections you have for any given image, it will be a long list, right? Because you might have multiple objects present. Now what you do is you first of all sort like all the detections based on the confidence score. Okay, so what you do is you go to the bounding box, which is like your model is actually very confident. It's saying like 100% this is a person. You start with that. Now what you do is you take that bounding box and compute the overlap of that bounding box with all the other detections. Okay, and the kind of overlap you will compute, it's called intersection over union. And again, this is a very important term. I think you're using for NMS, that's fine. But I think if you're solving detection problem, like whether you do evaluation, whether you like do some kind of loss computation, you will see like different variations of this intersection of over union. So try to understand like what this does. So first of all, you have two different detections. Okay, so there are two parts, numerator and denominator. So in the numerator, as the name says, intersection over union, right? So in the numerator, you will have intersection, and in the denominator, you have union. So intersection means what part of these two bounding boxes is common. And in this case, you can see like this blue region over here. That's the common part, right? So we just found, we find this area, whatever this area is, we put that in the numerator. And union is, we just combine like both the detections. And we just find like the area of this overlap, or not overlap, just like the union of these two bounding boxes, this blue color over here. And we put that in the denominator. So this intersection over union will tell you like what's the overlap between two different bounding boxes. Okay, so you do that for all the bounding boxes you have. You start with the highest one, and then what you do is if you find like there is like a high overlap between two different bounding boxes, you will keep like the highest scoring bounding boxes, but all the others you will just get rid of them. You will just remove them. You say that it's not detection anymore. Okay, now one trick here. So the trick is it's saying like high overlap. Now the question is, how do you define high overlap? And that's kind of arguable, and it will change a lot, like your performance a lot. And so again, this is like you can say a parameter. And even when we try to evaluate these object detection algorithms, later we will see we make use of this threshold as like one parameter. So we try to compute the performance of the algorithm at different thresholds. Okay, so this part is actually important. We will revisit this later. But for now, you can say that, okay, we have some kind of threshold. If IOU is, so this is going to be like between 0 and 1, right? So the best score you can get is 1, which means that it's a perfect overlap, because what will happen is Your intersection will be the area of the square, and your union is also going to be the intersection of that square because it's perfectly overlap. They are on top of each other. If the maximum score is 1, the minimum is 0 when there is no overlap at all. So union will be a big number, numerator will have completely 0. So then you can set a threshold, let's say 0.5, and say that, okay, if it's greater than 0.5, it's an overlap. If it's less than 0.5, you will keep both of the bounding boxes. Okay, so usually it's 0.5. Now let's try to understand with a simple example over here. Now this blue bounding box over here, let's say that was the bounding box which your model was saying with the highest probability this is a person. So we start with that and we compute the intersection over union of this bounding box with all the other bounding boxes. And clearly visually you can, if you inspect this, you can see that all these bounding boxes on the right, literally there is no overlap at all. So you will still keep those. But now if you look at these bounding boxes which are in the neighborhood, so some of these will have to go away. And again, that will depend on whether the intersection over union is greater than 0.5 or not. If it's greater than 0.5, you will just remove those. If it's not, you will keep those. And it may happen that if two individuals are standing next to each other, you might have like some kind of overlap between detections of those two bounding boxes, right? So in that case, we need this threshold. So one thing which you should understand here is this number 0.5 has nothing to do with like, although it's giving you like what's the overlap, but it doesn't mean that it's kind of 50% overlap, right? If it's 0.5 or if it's 0.75, it doesn't mean like the exact overlap is 3 by 4th. We will come to that, like how this number varies. Okay, so let's say this is the second bounding box with the highest second highest probability. And of course, so this we keep, so we just get rid of this. We don't use this for like future IUS scores because the IUS scores are not going to change, right? So we just save the computation cost. Again, for this blue box, we'll compute intersection over union with the rest of the bounding boxes. And again, we will get rid of the ones which are clearing this threshold. And you can see that some of these bounding boxes are actually overlapping, but the threshold might not be that high. So we still keep those. And you do that, keep doing that for all the bounding boxes. And finally, we get a result like this. So this is much cleaner. Okay, so that was the post-processing step. And you can see like already like this algorithm is doing pretty well. And then next, I think we'll see how we can evaluate like this kind of algorithm. So next, move on to the next segment, where we will talk about how we evaluate object detection algorithm. And so if your algorithm is saying for this particular image, like these all are people, then I mean, it's fine. Visually, we can say, okay, it's kind of doing a good job. It's missing some of the individuals. And some of these are like wrongly predicted. For example, this is not a person, right? We are missing on this, we are missing on this. But so we need a number, okay, a number between 0 and 1, which says that how good this algorithm is. And that's how we'll be able to compare like if we have multiple algorithms. Otherwise, just looking at this image, it's very hard. Okay, so we'll get that number and let's discuss like how exactly we can get that number. So before that, let's do a quick recap of intersection over union. We saw that earlier. Okay, so you will have two different bounding boxes. A yellow one is the intersection, which will go in the numerator, right? And the blue one is the union, which is like all the area these two bounding boxes are covering. And we just compute a ratio of these two. Now, again, we need like, so the threshold which we talked earlier, so there is a distinction. That threshold was for NMS algorithm. Okay, so the idea is you have your, so that was part of the algorithm. That was not part of your evaluation. Okay, so evaluation will start when you say that, okay, this is the model, these are the predictions. Then evaluation will start. And now we are talking about evaluation. But that NMS was part of your algorithm. All right. So that's like a clear difference. Now you have these detections. Now let's see like how the number looks like when the intersection over union score changes. In this case, you can select high overlap. You will get something like 0.9. And in this case, this is like something which I was saying, even the score is 0.5, it doesn't mean like it's completely half overlap, right? It's much bigger than that, but still you have a score of 0.5. And this is like 0.3, and it's going down, no overlap, you will get a score of 0. Okay, so this threshold over here is for evaluation, and usually you say that, okay, if you have set the threshold of 0.5 for evaluation, then what you will do is you will have the ground truth, let's say this red box, and this purple box is, let's say, your network's prediction. You will compute IOU, and this prediction is only correct two scenarios. Your class label should be correct. So your algorithm should be able to say, okay, purple box is actually a car, and you will compute this IOU, and then you will say that, okay, this IOU score is actually greater than 0.5. Okay, so that's the threshold. And this threshold we are going to use when we do the evaluation. Okay, so let's try to understand few terms before we go through the exact algorithm. The first thing is true positives, which means that, let's say the red bounding box is the ground truth and yellow one is like what your networks predicted. Okay, so in this case, first of all, as I said, the class label should be correct. Network is saying this this yellow bounding box is a bird, and the ground truth bounding box is also a bird, and the intersection over union of these two is greater than some threshold, let's say 0.5. Then this prediction is a true positive. And then there, of course, will be a lot of false positives. And again, there are a lot of variations there. Your intersection over union might be clearing the threshold, it's greater than 0.5, but then the model is saying it's a cat. Okay, so that's a false positive. Again, your network might be saying this bounding box is a bird, but the intersection over union is actually less than 0.5. Again, that's a false positive. And if there is no overlap at all, of course, that's a false positive. Okay. Now, the other category is false negative. And the idea here is you had like some kind of bounding box in your image, but your network was not able to see this image or this object. And it says, okay, no bird is present. It's not predicting any bounding box at all. So that's called false negative, because your network is saying nothing is present, but in fact, a bird was actually present there. And you can relate like these terms with, I think earlier when we were talking about recall, it's exactly the same idea. Okay, so one important point to note here is when we were talking about NMS, even though we are trying to suppress the nearby or overlapping bounding boxes, but again, as I said, that was part of the algorithm. Your algorithm might not be using NMS at all. Okay, so once your network has said, okay, these are the bounding boxes I have predicted, so you might still get like these kind of overlapping bounding boxes. Then the idea is, if you have two bounding boxes actually matching to the ground truth, where the class label is also correct, and the intersection over union is also greater than the threshold, which is 0.5. But still, only one of the bounding boxes will be counted as true positive. The other will have to go to false negative. And the reason is, ideally, essentially what I can do is I can just draw like bounding boxes all over this image and say that it's a person, it's a person, it's a person. And for sure, like I will be able to catch all these individuals here. But again, that's not like a right algorithm, right? It's giving a lot of false negatives. So that's why we need to make sure only one of the prediction is actually matched against the ground truth. Once you have matched the ground truth, that ground truth is actually out of picture. Then for future predictions, you will not have access to it, and it will be counted as false negative. Now, the precision and recall, the definition remains the same. It's not going to change. It's just like how you are computing your true positives and false positives. Okay, precision, is like a ratio between your true positives and you add like true positives and false positives. And recall is, again, you have true positives, but in the denominator, you have true positives and false negatives. And the concept remains the same. As I said, precision is how accurate your model is. Okay, if your model is saying there are 100 cats in this image, then out of those 100 predictions, how many predictions are actually correct? It doesn't matter if the algorithm actually missed 1,000 of other cats. So there might be like 1,000 cats in your image, okay, but your network only said like there are 100 cats. And if all those 100 predictions were correct, your precision is 100%. Okay, so precision will have value of 1. So precision is just computing how accurate your model is. It's not looking into the coverage. To look into the coverage, we have recall. So the idea of recall is, if you had 1,000 different cats, how many of those cats your model was able to predict? Okay, so for example, if you had 1,000 different cats and your model said like 100 different cats and all of those were correct, the recall will be only 10%. It will be 100 over 1,000. So in this particular scenario, your precision is 1, but your recall is 0.1. And that's why both precision and recall are important. You not only want to detect your objects correctly, you also want to detect all the possible objects. And a good example to think about this is, as I said in the previous slide, potentially what you can do is you can actually place the bounding box in all the possible locations in your image. Right. So in that case, you might have a very high recall because you will be able to detect like all the individuals there, right? But again, the precision will be very bad because a lot of those will be wrong predictions. Now, let's quickly go through the actual algorithm which is used to compute one number, which is called MAP score. You might have heard about that, mean average precision, but it's a little complicated, and I hardly doubt like anyone of you might know it. Some of you who are doing research, you might be aware of this. So pay close attention, like how it's done. It's a very simple algorithm, but it's a little tricky. Okay. So now we have seen you have the ground truths, which will be like a set of bounding boxes. And for each bounding box, you will have the class label. So that's category number 1. Then you have a second category, which is your model's prediction. Okay, so again, your model prediction will be like set of bounding boxes, and each bounding box, your model will say it's a cat, it's a car, or whatever category it is. So we start with those two sets. And what we do is, the first step is we just sort like all the predictions based on the confidence score. Okay, so, and again, earlier, I think we were doing this just for one image. In this case, we will do this for the whole data set. You might have thousands of images. You will just sort all those. Okay, you sort the prediction bounding boxes for all images according to the scores. And these scores is the confidence your model has on that prediction. For example, so this is like a sorted list, and these are the detections. So these are just names. Don't worry about it. So these are just like acronyms given to each detection. You can use whatever name you want. So don't worry about the second column over here. And again, don't worry about the first column as well. This is just like name of your image. And for example, you had like some image which is named image 5. You had some detection which was named R. You could use any other name. And your model said there is some detection, some object present in that image with a confidence of 95%. And that's the reason like this is on the top row, only because of this confidence score. All right. So that's the starting point. Now, once you have this bounding box, what you will do is you will compute the intersection over union of this bounding box with all the bounding boxes you have in your ground truth, right? And if there's a match, you will see like whether this bounding box is a true prediction or it's a false prediction. So once you have the intersection over union, you will see, okay, that's greater than threshold or not, greater than 0.5, right? And the class label should be correct. If that is the case, you have one true positive. And of course, you will have 0 false positives because you only have one sample at this point, right? So these are the two columns which are computing whether this particular prediction was correct or not. Okay, so either this will be 1, this will be 0, or this will be 1 and this will be 0, because your prediction can be either true positive or false positive. Now, these two columns are actually again true positive and false positive, but they are kind of accumulating these scores. Okay, so in this case, we have one true positive, so it's again 1 because prior to this we didn't have anything, and false positive is still 0. It will remain the 0. So using these true positive and false positive, not these scores, these are accumulated ones, you will compute your precision and recall. All right. So once you have that, then you you do this like for all the possible locations as you move down. Okay, so here you can see that, okay, the second one was a false positive. So your true positive remains the same. False positive becomes 1 because of this. Your precision will be half, and again, your recall will be this. So you keep computing precision recall for these accumulated true positives and false positives. Now, these are the numbers which we are going to use to compute the mean average precision score. And let's see how that's done. Okay, so this is called average precision. And the idea is you do this for like one class at a time. And you will have like similar curve for like all the classes. You just compute the average. And that average is called mean average precision. Okay, so let's see how this is done. You have like 1 point here, right? This is 1 and this is 0.06. You just plot this point in this chart. So let's say your first point was at this location because your precision was pretty high and your recall was like 0.06, right? And then you plot like the second point, which is again your precision was 0.5, recall was 0.06. This is your third point, fourth point, fifth point, sixth point, seventh, eighth, ninth, and 10th point. So these are actually just the points we have in this table. So these are like the XY coordinates you can see. All right. So once you draw that, you will see like it's kind of having this kind of trend because initially your precision might be high, but eventually it will go down. And what you do is you try to fill like the gap, because sometimes it may happen that you're starting from very low precision, then you go high. But what you do is you kind of backtrack. You just ignore that. Okay, so focus on this dashed red line. So whenever you are actually dipping, your performance is going down, you pick like the next highest performance and fill that gap. So you don't worry about this. And this will give you these kind of bounding boxes. Okay, you just ignore these lines, these steps. And this is going to give you like some kind of area where you can sum like the area A1, area A2, area A3, and this A4. And the sum of all these area of all these rectangles, again normalized, is called your average precision. The higher the number is, the better the algorithm is. And if you think about this, we have seen, I think, recall precision curve earlier as well. A better algorithm will be when you have high precision and you have a very high recall, which means that whatever your network predicts, it's almost correct, and it's actually able to predict all the possible detections you have in your data. Okay, so that's how you compute mean average precision. You just average across all the classes. As I said earlier, like this is like one of the most interesting lecture throughout this course. And I think we had like many other interesting lectures for classical approaches. But for deep learning, I think this is my personal favorite. And as I said, like the problem is not too simple, it's not too complex, it's like the right amount. And then the solution is, again, it's not very simple, it's not very complex, but it will give you like a very good flavor of what kind of solutions you can actually create for these traditional computer vision problems. And I think if you understood, like if you try to understand this pretty well, then you will be very confident to actually solve many different problems in computer vision. So last lecture, we discussed how object detection can be evaluated, okay, because that's really important. We can develop an algorithm, but if we don't know how good that algorithm is doing, it can be very difficult to actually come up with new algorithms, right? So that's one very important aspect. Then I think we discussed one very simple algorithm as well to perform object detection, and it was based on like simple sliding window. And later on, you will see like even in CNN, we actually do the same thing. And if you remember like the lecture from CNN classification, even though you have those kernels which are actually getting learned, but at the end, you are actually sliding those kernels throughout your image, throughout your feature maps. So that sliding window approach is like, I think, into the core of computer vision. All right, so now in this lecture, we will move on to like a CNN-based approach for object detection. And first, let's like get like a very simple flavor how we can actually just transform the classification problem to detection, and then we will move on to more advanced algorithms. Okay, so as we have discussed earlier, like the CNN, I think it started 2012, right? And so this is right here. And before that, we have like all classical approaches, all these. And so the y-axis is showing the MAP score, the mean average precision, which we discussed in the last lecture. And this tells you like how good your algorithm is doing. And the x-axis is showing like how this performance is actually improving over years, right? Every year, like it's moving maybe 1 to 2 points. And this performance is on like a very popular object detection data sets, which is called Pascal VOC. Okay, it's still used today. Now you can see like the performance was actually getting better and better with each year, and it's kind of saturated in 2012. And then I think after that we see like the deep learning boom, and I think 13, 14, it's like most of these methods are based on deep learning. And you can see like the rate of increase actually spiked a lot. Okay. So all this is like before CNN, and then these three are like, actually we're going to discuss these three algorithms in this course. Okay, so you know, like to train your models, whether it's object detection, whether it's classification, you need some kind of data set, right? And for that you need labels. Excuse me, let me just, I think one student is. All right, sorry about that. Okay, so any problem you solve in deep learning, you need data sets to train your networks. And as we discussed, like Pascal VOC is one, and then we have ImageNet detection. Then we have MS-COCO. MS-COCO is like I think most popular, which is used for object detection. And these are different like number of classes, which is like how many different object categories do you have. And then you have total number of images in these data set. You can see this is pretty small, just 20,000 images. But ImageNet, we have roughly 500,000. And MS-COCO is also pretty huge, like more than 100K. And this is showing you like how many objects you have on each image, right? So it's not just like one image, one object per image. You can have multiple objects, right? So in MS-COCO, you can see like the average is much higher. So this is kind of a dense scene in all these images, as compared to ImageNet, which is maybe just focused on single object. So this average is actually pretty low. All right, so now, so object detection, I think some of these questions we have tried to answer earlier as well. The goal of detection is not just to say that, okay, this object is present, but to try to localize exactly where that object is present. And it's not as refined as segmentation, where you give like the pixel-wise boundary, where you say that whether this pixel is this particular object or not. But it tries to give you like some rough estimation in form of a bounding box that this object is present in this location. And that's how like it can be differentiated from classification, where we don't care like where the object is present. All right. So now with these kind of differences between classification and detection, then you should now try to think what kind of output we will be requiring from our architecture if we have to solve detection instead of classification. So one thing for sure, we know that we need classification head, okay? Because we have to say that, okay, which object is present. Without classification, we can't solve detection. So which means that whatever classification was doing, we still have to do that. Now, in addition, since we have to also localize, which means that we need some more predictions from the network, and those predictions could be corresponding to these detections. Okay, so let's try to understand how that can be done. So one simple approach which can be taken to start from your classification model and extend it for detection, what you can do is you can take your deep network, okay, which was trained for classification. Now what that network will do is, given an image, it will just predict like the class scores. Okay, so if you have 1,000 different classes, each prediction will tell you whether that particular object is present or not. So if you have 1,000 classes, 1,000 different predictions, and you can use softmax for that. And considering like you only have one object present. So the idea is you will have some kind of CNN backbone. Then whatever extracted features you have, you try to flatten those features. And then you can add some like set of fully connected layers on top of that to get these predictions, right? And of course, like this is one variation. And I think in one of the lectures we discussed, it may happen that we don't need these fully connected layers, right? So you can have completely fully convolutional. But don't worry about that. That's perfectly fine. Whatever variation you have, the idea here is you have some kind of deep architecture which can solve classification problem for you. All right. So let's say we have this. Now, what we can do is, excuse me. Sorry about that. So now what we can do is, this is your backbone, which is fully convolutional, and it's extracting these set of features for you. And this is the same classification head where you had like, let's say 2 to 3 fully connected layers. Oh, sorry, this top one, fully connected layers. And it was giving you classification scores. So this is your classification head as usual, nothing new here. But now what you can do is you can add one more head. Okay, you can use the same set of features and you can add some fully connected layers on top of that. And you can ask those layers to predict the bounding box coordinates. And this could be solved as a regression problem. So it could be your regression head. Okay, so this is interesting because whatever features we're extracting for this image, they should have information about what object is present. And they should also have information about where exactly that object is present. And that's why these features can be used for classification as well as regression. Okay, so that's the idea. Now, let's say we do this. Now, this is a very simple modification of the classification architecture, right? And this is solving detection problem for you if you think about this. Because given an image, if you train such a network, this network can give you like which object is present. So that's solving the classification task. And it's also giving you like these bounding boxes coordinates. And again, these coordinates could be either center of the bounding box. And along with that, you might need like the height and width of the bounding box, right? So you just need 4 numbers. And I think we discussed this in the last lecture that for detection, you can have a lot of variations how you want to make predictions, but minimum you will need 4 numbers, right? So the other variation could be you can have, let's say, coordinate of the left top corner and the right bottom corner. Again, those will be 4 numbers. So the idea is to predict 4 numbers. And since you will have the ground truth, you can just compute like L2 loss or some kind of loss here to learn that. And once you have that, then this model will tell you, okay, exactly what are the coordinates of this object, and your prediction problem is solved. Okay, but let's see like why it's not so trivial. So okay, so this is fine. We just discussed that you can just train this using L2 loss because you will have the ground truth as well. And during test time, you will use both the heads. Okay. Now, now the issue is when you are doing detection of bounding box coordinates, right? So either you want to do like prediction of just 4 numbers, and then irrespective of which object is present, this head is always going to give you detection, and that's kind of class agnostic. Okay, so this head doesn't care about which object is present. Irrespective of that knowledge, this head is going to give you the localization of that object. So that's one variation. So that's called class agnostic. Okay, and for that you just need 4 numbers. It will give you 1 bounding boxes. Or you can have class specific prediction. So class specific means like then this network will care about like, okay, this bounding box is for this particular class. So which means like for each class, you will have a prediction. And that's like very well aligned with your classification scores. because for classification as well, for each class, you have some prediction. Okay. So in that case, if you have C number of classes, then you will need 4 numbers for each class. Then it becomes like C times 4 total numbers. All right. So in that case, the way it will work is during training, it's fine. You have the ground truth, you can train it. But during evaluation, what will happen is you will take a testing image. This will give you some prediction. And then you will see like, okay, which of these classes is actually highly active? And you will consider that as a prediction. For example, it says like it's a dog. So in this case, you will only look into the bounding box of the dog because you have for prediction for all the classes, right? So you focus only on the dog class, and that will be the bounding box. We just ignore the other prediction. All right, so let's move forward. So that was like a very simple extension of classification to solve detection. Now let's move on to like the first CNN-based approach, which was proposed for object detection. Okay, so this is like a real algorithm, and this is one of, I will say, like one of the breakthrough in object detection, and it has won like several awards as well. And even like many methods which are developed today are actually based on this this idea, and very simple idea, right? Now, and again, this is like what Mohammed just asked: what if we have multiple instances? Okay, so right now what we are doing is we are solving detection as a regression, right? So we might have multiple objects in the image. And in this case, like if you look at this image, we have a dog, we have like 2 different cats, right? And we have a duck. So if we have to solve this, we have to train a network for this. The regression task will be like these numbers. So these are like bounding boxes for each of these instances. And here you can see that you have 2 different instances of cat. So in total, these are 16 numbers. Now, if you look carefully, the earlier algorithm which we discussed, we had like C different predictions, right? For each, for C different classes. But in this case, for each class, for example, cat, we might have 2 instances. So, but we don't have that in the prediction, and that's the issue. This kind of simple approach will not take into account multiple instances which could be present in your image. Okay, so that's one issue. The second issue is, for this particular instance, you need 16 numbers because you have 4 different objects, right? Irrespective of which category. In this image, you only have 2 objects. So this will require just 8 numbers. Now, the issue is you know by now that when you are training your model, the network's prediction, it's not flexible. Okay, so if you have 1,000 classes to train on, you will always have to train for 1,000 classes. You can't say that, okay, this time I will train for 100 classes. This time I will train for 100,000 classes. It doesn't work that way because your network architecture is fixed and the whole training process is kind of fixed, right? Probably one day we'll come up with architectures which are kind of flexible, but we don't have that today, okay? So the issue is with detection, we need something where like the output is actually varying a lot. It's not just having multiple instances for each object category, but also having like multiple objects itself. Okay. So one simple solution to this problem could be, again, if you go back like what we discussed earlier, sliding window was very interesting approach, right? And we can try to solve your detection problem as classification problem. And that's exactly what we saw when we were trying to do sliding window. And the idea here is you take a bounding box and you say that, okay, if any particular object category is present or not. In this case, if this is a bounding box, cat is no, dog is no. You slide it, cat is yes, dog is no, right? So this is a classification problem now. And what we are classifying, we are trying to classify the features which you are getting from this bounding box. And this is like in very much alignment with the first algorithm which we studied for object detection, which was completely sliding window, right? Okay, so that's like exactly sliding window. Now let's try to understand what are the issues with this algorithm. So first of all, we have to test like each and every possible location. And you know, if the resolution of image will increase, those locations will increase. So there is some scalability issue. And not just position, you also have to test different scales so that your algorithm is scale invariant, right? So which further which further like increases the computational complexity. Okay, so different scales, you have to search different positions. Now, this algorithm, and again, you will be surprised like the solution they have. You only have to look at like only subset of possible solutions. And that was the solution. Exactly, that was the solution. You don't look at all the possible locations, but look at only a few set of locations. And it will solve the issue of this scalability. And that's what faster RCNN actually did. Not faster, the RCNN actually did, the first version of that algorithm. Okay, so let's see how that can be done. So the basic idea was coming up with this region proposals. And again, this is something which we have like discussed a lot in this course, how to find like the interesting points. SIFT used to do that, right? And we have like many other algorithms to do that. I think we also studied corner detection, Harris corner detection, that also gives you the salient points in your image. So that was the whole idea. What if we don't scan all the possible locations, all the possible scales, but we use some algorithm to actually subsample this space for us? For example, if this is your input image, we will run that algorithm, and that algorithm will tell you, okay, these are the places which are like most likely where objects are present. Okay, and it will also give you some kind of scale as well. So now if you think about this, in this scenario, you have like a lot of different scales, right? The smaller bounding box, you have the bigger bounding box. Some of these bounding boxes are actually perfectly covering the objects, cat and dog. Some of these are covering the flowers, some of like the nose, the eyes. So we have a lot of variations. But if you count these are just like handful, maybe 10, 12, or 15 different bounding boxes. As opposed to if you have used like all these scales, then if you have slided those variations in this input image, that would have given you thousands of locations and variations. Okay, so that's the crux of this first algorithm. You subsample your search space. And of course, there are a lot of algorithms to do that. And in their work, I think the first work, they used this selective search algorithm. And again, we don't have to go through like the detail of this algorithm. The idea was just like to select key points, which will give you these region proposals. So these are called region proposals. And the architecture was called region proposal network because it was utilizing these region proposals. Now, I think this, we can quickly go over this. The idea was you perform some kind of segmentation, and we're going to talk about segmentation later in the course as well. So don't worry about how this can be obtained. We'll cover some algorithms for that as well. But the idea is it tries to group like pixels together for similar objects, right? And again, we can do that at multiple scales. This is looking at fine level details. Again, this is coarse level, and this is even coarser. And once you do that, then you can convert these regions, or you can say like superpixels or segments, into these kind of proposals. So then what you have in the bottom, these are your region proposals, and you will only look at these possible locations. Okay, so this reduces like the computational complexity a lot. Now let's try to understand how that can be used in this deep learning kind of architecture. And of course, there are some limitations which we'll cover later on. So this architecture is called RCNN, and R is for region proposal network, and CNN is for convolutional neural network. And CNN is because we are using like features which are extracted by CNN architecture, and R is like we are using subsampled region proposals. Now, what we do is, given an input image, we first run that pre-processing algorithm, which will give you these region proposals. Okay, it will give you like all the bounding boxes, possible locations with different scales, varying scales. Now, what you do is for each bounding box, you will actually try to warp that image. So what you will do, you will actually make sure that you reshape all the proposals into same resolution. And you can, that's a parameter of the architecture. You can say, let's say this is 28 cross 28. So all the region proposals will be reshaped to 28 cross 28. Doesn't matter like what was the original size. Okay. And I think roughly the idea is to use around 2000 proposals, which is again not very small number, but again not very huge number. But it covers like most of the variations you can have in your input images. And again, that's like one parameter which you can change. You can try like fewer proposals as well. You can try more proposals as well, depending upon like what kind of images you have in your data set. Okay, so that's the first step. You resize them. And once you have resized, then you have your CNN architecture. And you know that CNN architecture takes like images of fixed size. And now you have make them like of fixed size. So you pass them to the CNNs and you will get the features. Okay, so once you have the features, you train your classifiers on those features. And in this case, the classifier which was used was support vector machine. And we have discussed support vector machine, right? The input to support vector machine is some set of features and you train it for classification. Now, let's see how this kind of approach can solve detection and classification simultaneously. Given an image, you will have lots of proposals. Everything will be resized to the same resolution, passed to the CNN, and that CNN will give you features which you will pass to a SVM, which is a classifier, and that classifier is going to give you which class is present. And it's also going to give you some kind of adjustment to the bounding box. Okay, so this second prediction is corresponding to the location of your object. Now I will explain like why exactly we need this bounding box regression. But before that, let's first try to understand like how this is working. Now we talked about sliding window algorithm, right? And we talked about like converting detection to classification problem. And this is exactly doing that because you are looking at like a very smaller crop of the image and you're just classifying whether in this crop, this object is present or not. For example, if you have 1,000 different categories, this SVM is going to classify like those 1,000 categories. Okay, so this becomes classification problem. So now you know that what object is present in this particular region, and in this in a way it's actually also giving you the location. Okay, but in reality what happens is this location is not perfect. You might need some kind of adjustment to it, maybe rescaling the bounding box or moving it slightly, some adjustments, right, to make it more perfect. And to do that, we need this bounding box regression. And this prediction is just telling you, given the location of this bounding box in the input image, how should I adjust those points so that the prediction is actually better aligned with the ground truth. And again, you have the ground truth, so you can compute that loss. Okay, so you do that for all the patches here, all the 2000 patches. And that's how you solve your object detection problem using some, you can say it's not completely deep learning, but in a CNN way. And that was the first algorithm and it worked really well. Okay, so regions roughly 2000, as I said. And so as a backbone, I think AlexNet was used because that was the architecture which was available at that time. And it was pre-trained on ImageNet dataset where we have 1,000 different classes. And you know, like ImageNet at that time, it was just for classification. So later it had to fine tune with Pascal VOC, which is object detection dataset. Okay, so these are some statistics of that architecture. We can quickly go with these. Yeah, so this step is fine. You resize your patches. And FC7 is just like one layer of your AlexNet, right? If you remember from one of the lecture. And the number of neurons in this layer was 4096. Again, that's just a stat. And you use this as input to your SVM, which is going to give the classification, which class is present actually in each of these patches. Okay. Now quickly go over like the steps, like you try to understand like how cumbersome this was. The first step was you have to get like this pre-trained model, these weights, right, which was trained for classification. And then the second step was you will have to create like a new layer, because imagine it was 1,000 classes, but your target data set, let's say, which is VOC, there were I think only 20 classes. So you will have to change that. And again, these are just technical details. And then I think this was pretty huge thing back then. You had to extract features actually for all the region proposals, and you have to save them on disk. Okay, it was a different world back then. So for all the proposals, like you have roughly 2,000 proposals for each image. So you resize them, you pass them to the pre-trained network, you extract the features, and you save to disk. So for Pascal VOC, it was roughly 200. In these days, 200 gigabytes, it's not a lot, but back then it was a big deal. Okay, so once you have those training features, then again, this is the same process what we discussed for the sliding window approach. Now, each batch, you have the feature and you have the ground truth of the detection, right? So you can say that, okay, this is the true class or not. For example, if you're looking for cat, then these are the positive samples. Then you will also mine some negative samples. This is not a cat, not a cat, not a cat, right? And what you do is for each class, you train a binary SVM. So if you have 1,000 different classes, 1,000 different SVMs, VOC has 20 different classes, so 20 different SVMs. Again, which is kind of cumbersome, not that trivial. Okay, so this will be like the training data, which will look like something like for dog. This is the positive sample and all these will be negative. Now, so that was for classification. Now let's quickly look into like how regression adjustments were made. Now your region proposal will give you the bounding box, right? Something like this. And if that bounding box is perfectly aligned with your ground truth, then your proposal is pretty good. So what you will predict is 0, because you don't need any adjustment. Okay, but it might be something like this, not completely aligning with your ground truth. You need some kind of adjustment. And again, this adjustment, like it's up to you, like what you want to predict, right? Because you have the bounding box for the proposal, you have the bounding box for the ground truth. It's up to you how you want to align them. And this is just one way. And I think what this is trying to do is 0.25. So this, I think, is just saying that you shift your X coordinate to the right by this much amount, 0.25 amount. Okay, then it will perfectly fit. Okay, so it's slide towards right. But again, that's just one way to do the adjustment. You can have like many other variations here as well. In this one, I think it's saying negative of this. Of course, we have it here, right? Okay, so in this case, what it's showing is, so we have 4 different numbers for adjustment, right? And the first number is how much should you shift your X value, right? So this is 0.25. So you will shift X to 0.25. And the Y is telling you like how much you should shift in the Y direction. And the W and the H is like how much you should change your height and width. So these 4 combinations actually cover all the adjustments you might need. For example, in this case, it's negative. So it's saying that your bounding box is actually too wide. Make it a little thinner by that much amount, and then it will fit perfectly to your ground truth bounding box. Okay, so the second prediction, which was the bounding box regression head, you will have predictions like this. Now let's see what are the challenges or what are the like issues with this RCNN, and that will lead us to fast RCNN, which is the next in this series. Now there are actually not one, several issues with RCNN. First of all, it's very slow during runtime. Okay. And the reason for that is you're actually getting multiple proposals. Okay. So, and these proposals can be overlapping. And there could be a lot of overlap, because you can assume that this is a very small image. And if you're getting 2,000 proposals, there is going to be a lot of overlap. And what we discussed earlier in RCNN, for each proposal, you're actually extracting a feature, right? Because each each region proposal, you reshape it and then you pass through the CNN to extract the feature. So if you think about this, if you have 2000 proposals in an image, you are actually doing that feed forward step 2000 times, which is actually not required. A lot of that is redundant. Okay, so that's first issue, and we will see like how that can be solved in fast RCNN. And the idea is, instead of having multiple passes, we just do a single pass for each image and extract features. And again, that's a very, very interesting concept. Okay, before talking about that, we have like, I think one or two more issues. Second issue is we have to train like separate classifiers or separate SVMs for each class category, which is not efficient. I mean, with 20, it was 20 classifiers. With 1000 objects, it will be 1000 different classifiers, right? So it's not scalable. Now, the idea was how we can fix that, and we can actually do end-to-end learning where we don't need SVMs. Okay, so that will be the solution. The third issue was the complex training pipeline, because first you have to like figure out what are the region proposals. Then for each proposal, you reshape, you extract features, save features, then again load features, train your SVM classifier. Very, very complex pipeline, right? So we'll try to simplify that a little bit. And what we'll need is like just a single forward pass for each image, which will do like all of this together. Okay, so the solution is it's called fast RCNN, and we have three different items to discuss here. We will do like a single forward pass instead of multiple passes. We won't be having like separate classifiers for different classes, and it will be like end-to-end learning. Okay, so this is like again similar kind of architecture. Now the interesting part is, instead of applying like the region proposals on the input image, we apply these region proposals on the activation maps. So we take the input image, pass it to CNN, extract the features. Let's say this is your activation feature activation map. So these are already your features. Now on top of, since like your CNN can preserve the spatial structure, right? So then you can actually apply these region of interest, or you can say maybe some kind of region proposals on these activation maps. And instead of reshaping like your input sample or input image, you reshape these features. And what we need for that is called ROI pooling. This is a region of interest pooling. You will heard like this term a lot. Okay. And this ROI pooling is required because the same way we need to reshape like your region proposals to same shape, we need to do the same thing here as well, because your different feature sets should be like having same dimensionality, right? So for that, we need ROI pooling. We'll discuss about how exactly this is done. So once that is done, then each of these regions will have like same number of features, which again you can flatten and use them as features and directly do classification. So this is your softmax classifier head, and this is again a linear layer, which is giving you bounding box regressions. Okay. Now in this case, we don't need like separate SVMs. So this is end to end, and we don't have to pass like the patches like independently through your CNN. It's just done once. These two steps are mainly optimized. Okay, so it will look something like this given your input image. Let's say if this is your region proposal, you will first extract features from your image and then apply this proposal on that feature map. So we'll have to do some kind of scaling, because the resolution of your feature map will also reduce, right, corresponding to your input image. So you'll have to perform same kind of scaling to your bounding box as well. And then you will use features only from that location to bring them down to a certain shape. And that step is called ROI pooling. And rest, I think, is trivial. You have those features, you make softmax predictions, you can make like a bounding box regression. Okay, so this is same, but it's just like you don't need SVM for that. You're using neural network for it. Now, I think this part was easy, how this can be done end to end, because instead of training SVM, we are just training neural network. This part is something new, so let's spend some more time on this. Okay, how to perform region of interest pooling. Now, given an image, you extract feature map. If your input image is 3 cross 800 cross 600, 3 is like for 3 different channels of a color image. So after extracting features, it might reduce to C times H times W, right? This is height, this is width, and again, this is number of channels you have. And again, it will vary from like network to network, but still you have this kind of spatial structure. And in a way, we can say that, okay, in this height and width, each location, we can say that, okay, which region this pixel belongs to, okay, or this activation belongs to in the input image. And that is called receptive field. So not exactly receptive field, but there is some correspondence. Receptive field is actually what different pixel values were actually used to obtain this activation. And usually like in CNNs, if you go deeper, your receptive field is like the whole image. Okay, so that's slightly different, but the idea is to find one-to-one correspondence. So in this case, you know that how much of your image has downsampled because you know these numbers and you know value of H and W. So we'll perform same kind of transformation to your proposal box as well. We'll try to fit it here on the feature map. And then you will try to extract these activations into like a fixed grid, which will have, let's say, a shape H cross W, because we want to bring all the proposals to same resolution. Okay? Something like this. Of course, number of channels is not going to change, but what's changing is the shape of this. If it's H cross W, it's coming down to small h, small w. So ideally at the end, it doesn't matter like what was the shape of your proposal in the input image. Every proposal will have feature vector, or you can say activation map of this shape, C cross small h cross small h. Okay, so let's try to understand how this step can be done. And of course, you can backprop through this because this is kind of max pooling operation we are doing here. And you know, max pool is differentiable. All right, so this is your input image, and let's say this is your proposal. And of course, you are creating those proposals. You will have the dimensions, the height and width, and the exact location. And you will try to map that exactly on the activation map. Let's say your input image is 600 cross 600, and your proposal is like 200 cross. This is something 145. So don't pay too much close attention to exact number, but just try to understand the concept. And let's say the image resolution is actually going from 600 cross 600 to 16 cross 16. This is your activation feature map size. So if you try to map this bounding box over this, it will lie something like this. Now, the tricky part is, since the resolution of your image has reduced a lot, which means each location in this grid actually corresponds to multiple pixels, right? And because of that, this bounding box will not perfectly align with this grid. Okay, so now the question is, if you have to do max pooling on that, how do you make adjustments? And there are different ways. I mean, you can try to increase the size and try to fill it properly. And usually I think a ceiling operation is used. So if it's here, you just find like the closest corner. Okay, so that will be the adjustment you will have to make. So the red one is the actual proposal in your input image, but after adjustment, it becomes like this orange region over here. Now, if you think about this, some of these pixel values over here were used to extract these activations. But in fact, we are not using that after ROI pooling operation. And that's kind of one of the limitation. We are actually losing information. And if you pay attention to like this region here, this is like additional information which we didn't want, because these pixels actually lie outside this bounding box. So kind of if you look at the green region, that's something which we didn't want, but we have to sacrifice with that. And again, blue is something which we wanted, but we have to get rid of that. And so that's like one way how you lose information. There is one more way how you lose information. For example, if you have activation, something like this, activation map. Okay, so this is in this case 4 cross 6 area. and we want to map this to 3 cross 3. Okay, so what you do is you try to divide this into like 3 cross 3 grid, and you just perform max pooling. Okay, so these 2 pixels, you pick the max one, and again, these 2 pixels, you pick the max one, and you can pick like average pooling as well. It's perfectly fine. You can have different variations, but you will have to ignore the last row because that's kind of not fitting into picture, right? How will you use that information? Because it's not actually completely dividing. So again, this is loss of information. So multiple ways like how we are losing information, and later we will see like how we can address this. But at least in fast RCNN, this is how it was done. Okay, so this is like the lost data, which is fine. Now let's try to compare with, some stats between fast RCNN and RCNN. In terms of training time, it took like roughly 84 hours. Okay, and again, this is VOC dataset. Fast RCNN reduced that to just 9 to 10 hours. Okay, so a lot of reduction in training time. So again, testing time, it was 47 seconds, and you can see like it's fraction of a second. And performance, it's like almost the same, 66 and 66.9, not a huge improvement. But if you look at these numbers, these are amazing. And you can guess like why this happened, because we saved like a lot of computation costs there, right? So let's continue. And this is, I think, the last segment we have in object detection. And in this one, we will talk about faster RCNN. And this will try to overcome like the limitations we have in fast RCNN. So first try to understand like what are those limitations. So I showed you like those impressive numbers, right? How fast RCNN was. But if you think about this, even before like starting training this model, we need to run like some kind of region proposal network, right? Or you can say some kind of region proposal estimation. It could be selective search or something else. And that requires a lot of time. And those numbers which I showed you, they didn't include that computation time. So the idea was, do we really need like some external function or algorithm to detect those region proposals? Can the network do this for us? Okay, and that's what was tried in fast RCNN. And this is again 2015. And the idea was we use like the CNN architecture to actually make these region proposals for us. And with this, we don't have any external dependency. The whole algorithm is actually completely end-to-end. And that's pretty neat. Okay, so the idea was you have your image as input, you pass it to CNN, you get the feature map, right? Then what you do is you have these region proposals. Okay, so these are like some kind of proposals which you pre-estimate, and you try on these feature maps, and then you train a classifier which will tell you, okay, whether this is a proposal or not. And it could be just like a binary classifier. Okay, and it will just tell you whether at this particular location object is present or not. Okay, so, and again, so the interesting thing was like the CNN backbone you will use for like extracting feature for your image can be shared with this region proposal network, which is going to give you these proposals. Okay, and again, that's pretty simple idea. You can see it's just like using same features and just predicting like one more value, right? Now, one catch there was we had to use like these anchor boxes to train this kind of architecture. Okay, so which will tell you like whether the object is present or not. And these anchor boxes were like of different aspect ratios and different scales. And the idea was so that we cover like the different variations we can have in our input image. Okay, so aspect ratio were like, you can see like we have square, and then we have this vertical rectangle, and then this rectangle over here, just horizontal. And then again, these 3 variations and 3 more different scales for these. So what we do is we put these anchor boxes on the features which are extracted by the CNN, and then that will tell you whether this is this is like a proposal or not. Okay, it will tell you like either yes or no. And if it's yes, then you will use that as a proposal. Okay, so these will be your anchor boxes, 3 different aspect ratio, 3 different scales. And of course, you can assume that, okay, this seems like very restrictive, but remember, this is just your proposal. At the end, you're also going to have like your bounding box regression, which will do some adjustments to actually fit this anchor box into the actual ground truth. So we have that adjustment, and that's why it's fine to have like just 3 different scales and 3 different aspect ratios. Okay, so this kind of architecture, it's called a region proposal network because it's giving you these region proposals, right? And you can see like for each anchor box, we have these 2 different predictions. The first one is the classification layer, which is giving you whether this anchor box is object or not. And the second prediction, again, this is a regression. It's trying to adjust like that bounding box to the ground truth. Okay, so, and again, that was trained like separately. These days, you can train this like simultaneously as well. And then once you have that, will give you region proposals. And then, so again, this is just a replacement of your selective search. The rest of the things will remain the same from your fast RCNN. That's not going to change. Okay, so the idea was just to get these proposals inside the network itself. Okay, so RCNN was the beginning, like how you can use CNN for object detection. Fast RCNN tries to improve it in terms of computation time, and faster RCNN, it tries to make it like completely end-to-end, where we don't have any external dependency for region proposals. Now, there was a question, I think, how this was extended to mask RCNN. And I think it's a pretty simple trick. You take these proposals, these detections, right? And you extract these features the way you do for classification. And then you try to predict like the segmentation mask, the exact boundary for that. So the prediction will be like a pixel-wise prediction, whether this is object or not. So it could be a binary mask. Okay, so it's kind of trying to, given a bounding box, you have the rough location. Now you have to find the exact boundary. It's a very small network, small CNN architecture you can use for that. And of course, if you have the ground truth, you can train that thing, right? So that was the extension for mask RCNN. There were some other optimizations as well, and of course, we are not covering those, but that was the main difference. All right, so I think that concludes the lecture on object detection. If you have any questions, please let me know.